Light is the fastest thing in the universe. You've known that your entire life. It's one of those facts that sits so deep in your understanding of reality that you've never once questioned it. Light travels at 299,792 kilometers per second. Nothing beats it. Nothing even comes close. But here is what nobody tells you. At that speed, the ultimate speed limit of the cosmos, crossing from the nearest star to Earth would take over 4 years. Crossing our galaxy would take 100,000 years, and reaching the nearest galaxy cluster would take hundreds of millions. The speed of light isn't fast, it's a prison. Every science classroom on Earth teaches the same foundational fact. Light travels at approximately 300,000 kilometers per second. More precisely, 299,792.458 kilometers per second in a vacuum. It is the universe's absolute speed limit, enshrined in Einstein's special theory of relativity, confirmed by over a century of experimental verification, to a degree of precision that makes it one of the most tested and trusted constants in all of physics. And in the context of our everyday human experience, that speed is genuinely incomprehensible. Light circles the Earth roughly 7.5 times in a single second. It travels from London to New York in approximately 18 milliseconds, faster than a human nerve signal can travel the length of your arm. If you could move at the speed of a light, you could cross the continental United States roughly 1,000 times in the span of a single heartbeat. Against the backdrop of human experience, the speed of a light is infinite, instantaneous, beyond any meaningful comparison. This is where the comfortable lie takes hold. Because we absorb this fact, light is unimaginably fast, and we carry it forward as a kind of reassurance. We map the speed of light onto our human intuitions about what fast means, and we conclude that the cosmos must be, in some functional sense, navigable, reachable, that the universe's speed limit, while technically finite, is finite in the way that the top speed of a race car is finite, technically bounded but practically sufficient for any purpose you might reasonably imagine. Then you actually do the math, and the reassurance evaporates. The nearest star to our Sun is Proxima Centauri, a red dwarf located approximately 4.24 light-years from Earth. A light-year, the distance light travels in 1 year, is roughly 9.46 trillion kilometers. Multiply that by 4.24, here's when Proxima Centauri sits at a distance of approximately 40 trillion kilometers. A spacecraft traveling at the speed of light would take 4.24 years to reach it. Our fastest actual spacecraft, the Parker Solar Probe, which at its perihelion reaches speeds approaching 692,000 kilometers per hour, would take over 6,000 years to cover the same distance. 6,000 years to reach the nearest star. What does 6,000 years mean in human terms? It means that a spacecraft launched at the dawn of recorded civilization, when the first Mesopotamian city-states were forming, when the Egyptian Old Kingdom was still a millennium in the future, when Stonehenge had just been completed, would be arriving at Proxima Centauri approximately now, and Proxima Centauri is next door. Cosmically speaking, it is the house across the street. So already, before we have left the immediate neighbourhood of our own solar system, the speed of light has revealed itself not as a liberating constant, but as a confining one. The universe's fastest possible speed produces travel times measured in millennia to reach our nearest neighbour. What does that imply for the galaxy? For the universe beyond the galaxy? Our Milky Way galaxy spans approximately 100,000 light-years in diameter. Even travelling at the speed of light, the absolute maximum allowed by physics, crossing from one side of the Milky Way to the other would require 100,000 years. Our galaxy alone contains somewhere between 200 billion and 400 billion stars. The nearest galaxy of comparable size, the Andromeda Galaxy, sits 2.537 million light-years away. A journey there, at the speed of light, would take 2.537 million years. The observable universe, the sphere of space whose light has had time to reach us since the Big Bang, spans approximately 93 billion light-years in diameter. A journey from one edge to the other at the speed of a light would require 93 billion years, more than 6 times the current age of the universe. These numbers don't inspire wonder in the way that the discovery of a new exoplanet or the image of a distant nebula does. They inspire something quieter and less comfortable, a growing sense of enclosure, of walls closing in at an imperceptible rate. Because what these distances reveal, when held alongside the speed of light, is not the grandeur of a cosmos waiting to be explored. They reveal the grandeur of a cosmos that is, for all practical and perhaps even theoretical purposes, sealed. And here is where the question that should truly unsettle you begins to take shape. We have spent decades scanning the sky for signals from other civilizations. The search for extraterrestrial intelligence, SETI, has been listening to radio frequencies, analysing stellar spectra, cataloguing anomalous signals since the early 1960s, when astronomer Frank Drake pointed the 26-metre radio telescope at Green Bank, West Virginia, toward two nearby sun-like stars and listened. We have found nothing definitive, and one of the standard responses to that silence is a kind of patient optimism. They're out there, we just haven't found the signal yet, or they're too far away, or we're not looking in the right frequency. But consider a different possibility. Not that we haven't found them, not that they don't exist. Consider the possibility that the speed of light, the universe's own speed limit, makes any meaningful contact or travel between civilizations not merely difficult, not merely unlikely, but physically, mathematically, cosmologically impossible at any scale that human civilization could survive. Consider the possibility that the universe built a cage, set the speed of its own bars at 300,000 kilometers per second, and called it a law of physics. That is not a poetic exaggeration. It is a sober description of what the equations of general and special relativity, when applied honestly to the actual distances of the cosmos, produce. But here is what makes this more than a simple exercise in discouraging arithmetic. The story of light's cosmic speed limit is not merely a story about distance. It is a story about time, about causality, about the fundamental structure of space-time itself, about what it means for two civilizations to exist in the same universe but in such radically different cosmic addresses that no message, no ship, no signal they send to each other could arrive within any timescale relevant to either civilization's continued existence. It is, in the most precise and literal scientific sense, a story about cosmic loneliness. The physicist and cosmologist Brian Greene has described the situation with characteristic precision. The universe is not merely large, it is large in a way that specifically defeats the tools available to the creatures inside it for crossing it. The speed of light was not set at a value that permits galactic civilization. It was set, or rather it simply is, at a value that permits local planetary chemistry, local solar system dynamics, and absolutely nothing beyond that at any humanly relevant timescale. And the deeper we look into what that means, for the Fermi paradox, for the search for extraterrestrial intelligence, for the long-term trajectory of any technological civilization in this cosmos, the stranger and more profound the implications become. Because the speed of light being a prison doesn't just affect us. If the universe contains other civilizations, and the mathematics of probability suggests it almost certainly does, then every single one of them is in the same prison, isolated, separated, unable to reach their neighbours at any speed that their civilization, their culture, their language, their very biological continuity could survive. A universe full of life, and none of it able to find the others. But that's not the full story, because the speed of light is not simply a barrier to crossing space. At the distances we're discussing, it becomes something even more disorienting, a barrier to crossing time. And the implications of that truth take us somewhere far stranger than a simple calculation about travel distances. What scientists found when they followed this thread to its logical end would shock even the researchers who had spent careers thinking about it. To truly understand why the speed of light functions as a cosmic prison rather than a cosmic highway, we need to spend time with a concept that most science communication glosses over in its rush to get to the exciting parts. That concept is the light cone, and it is, without exaggeration, one of the most important geometric ideas in all of physics. In Einstein's relativity, space and time are not separate things. They are woven together into a single four-dimensional fabric called space-time. Every event, every point in space at a particular moment in time, exists within this fabric, and every event has associated with it two invisible structures that physicists call the future light cone and the past light cone. Picture it this way. You're standing at a point in space-time, a particular location at a particular moment. The past light cone is the complete set of all events in your past that could possibly have influenced you. all the points in space and time from which light, travelling at 299,792 kilometers per second, could have reached you by this moment. Your past light cone defines everything that is causally connected to your present. Your future light cone is the complete set of all events that you can possibly influence. All the points in space and time that light leaving you right now could reach in the future. Everything outside these cones, all the events that are too far away in space for light to have travelled between them and you in the time available, is causally disconnected from you. Not merely unreachable, causally disconnected. No information, no signal, no influence of any kind can flow between you and those events. They are, in the language of physics, space-like separated, and space-like separation is not a technological barrier. It is a structural feature of reality itself. Here is what this means in practical terms. Right now, at this moment, the vast majority of the observable universe is outside your light cone in any operationally meaningful sense. A civilization on a planet orbiting a star in the Virgo cluster, 65 million light-years away, is causally disconnected from us in the sense that any signal they send today will not reach us for 65 million years. Any response we send to that signal will not reach them for another 65 million years. A full round-trip communication, the cosmic equivalent of sending a letter and waiting for a reply, would take 130 million years. 130 million years ago, Earth was in the late Cretaceous period. Dinosaurs had another 65 million years of existence ahead of them. Our primate ancestors would not appear for another 100 million years. The species that is now capable of asking whether anyone out there is trying to communicate did not exist, in any recognizable form, 130 million years ago. What civilization survives 130 million years to complete a single exchange of information with its neighbour? This is not a rhetorical flourish. It is a genuine constraint that the structure of space-time imposes on communication between any two civilizations, separated by tens of millions of light-years. The question of whether alien civilizations exist becomes almost secondary to the question of whether the concept of contact between them, any kind of contact, even a radio signal, is meaningful at the distances involved. And we are still talking about relatively nearby regions of the observable universe. The Virgo cluster, at 65 million light-years, is essentially in our cosmic backyard. Now let's talk about the expansion of the universe. Because here is where the situation transitions from merely discouraging to something genuinely, philosophically vertiginous. In 1929, astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, published observations demonstrating that distant galaxies are receding from us, and that the farther away a galaxy is, the faster it appears to be moving away. This was the observational foundation of what we now call the expanding universe. Space itself is stretching. The fabric of space-time is growing larger, carrying galaxies along with it the way dots on the surface of an inflating balloon move apart from one another, even if no dot is moving across the balloon's surface. In 1998, two independent teams of astronomers, the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project led by Saul Perlmutter, made a discovery that earned them the 2011 Nobel Prize in Physics. Using Type 1, A supernovae as standard candles to measure cosmic distances with extraordinary precision, both teams independently found that the expansion of the universe is not merely continuing, it is accelerating. Something, given the placeholder name dark energy, because we genuinely have no idea what it is pushing the universe apart at an ever-increasing rate. The expansion is speeding up. This has a consequence that strikes at the heart of any hope for intercivilizational contact across cosmic distances. Because if space is expanding, and if that expansion is accelerating, then distant galaxies are not merely moving away from us at some fixed velocity, they are accelerating away from us. And beyond a certain distance, called the Hubble radius, currently approximately 14.2 billion light-years from Earth, galaxies are already receding from us faster than the speed of light. This is not a violation of Einstein's speed limit. Nothing is moving through space faster than light. What is happening is that space itself is expanding, stretching the distances between objects. The cosmological recession velocity of objects beyond the Hubble radius exceeds the speed of light not because anything is travelling faster than light, but because the space between us and them is increasing faster than light can cross it. the practical consequence is absolute. Any light, any signal emitted today from a galaxy beyond the Hubble radius will never reach us. The space between us and that galaxy is expanding faster than the light can travel across it. The signal chases us, but the distance keeps growing. It will never arrive, and the Hubble radius is not fixed. As dark energy continues to accelerate the expansion, more and more of the universe crosses that threshold. The observable universe, the sphere of space from which light can still reach us, is not growing. It is shrinking, slowly, inexorably. Over timescales of hundreds of billions to trillions of years, galaxies that are currently visible to us will recede beyond the Hubble radius and vanish from our observable universe entirely. The cosmic prison is not merely static, it is contracting. To put this in perspective, astronomers estimate that roughly 94% of the galaxies in the observable universe are already receding from us faster than the speed of light. Right now, today, the overwhelming majority of the universe's galaxies are beyond any possibility of physical contact, not because of any technological limitation on our part, but because of the fundamental geometry of an accelerating, expanding cosmos. We can see them. Their light, emitted billions of years ago when they were closer, still reaches us. But that light is a message from a past that no longer exists, from a location that is now beyond reach. We are looking at ghosts of positions that galaxies have long since abandoned, and those galaxies are now racing away from us in directions that no ship, no signal, no force in the universe can overcome. What does it feel like to know that? To genuinely sit with the understanding that the vast majority of everything that exists is already, permanently, irrecoverably beyond any possibility of contact. It feels, if you allow yourself to engage with it honestly, like standing in a room and watching the walls slowly close, not quickly, not dramatically, but with the patient, absolute certainty of physics operating on cosmic timescales. And yet here is where the story takes its first unexpected turn. Because we have been discussing these distances as though the speed of light is simply a fixed, immovable, eternal constant, as though the prison's bars are made of something inviolable. But what if they aren't? What if the universe, in its extraordinary complexity, contains within its own laws the seeds of what appears to be a possible escape? The implications of this are staggering, and we'll explore that in just a moment. But first, we need to understand exactly how the prison was built, and why the beings who discovered its architecture have spent decades arguing about whether any door exists at all. Physics has a peculiar relationship with the word impossible. Throughout history, the things that physics has declared impossible have occupied a fascinating spectrum. Some have proven genuinely, permanently impossible, while others have turned out to be merely extraordinarily difficult, or impossible only within a framework of assumptions that later turned out to be incomplete. Heavier-than-air flight was considered by serious scientific thinkers to be impractical at best. Nuclear power was described as a fantasy by Ernest Rutherford himself, the man who first split the atom, just 1 year before it was demonstrated. The 4-minute mile was considered a physiological barrier until Roger Bannister crossed it in 1954, and then several dozen people crossed it within the following year. Faster-than-light travel, by contrast, occupies a uniquely uncomfortable position in the landscape of declared impossibilities. It is not merely an engineering challenge or a question of available energy. The prohibition against superluminal travel faster than light, is embedded in the mathematical structure of special relativity in a way that appears, to the best of our current understanding, to be genuinely fundamental. Not a wall we haven't yet found a way over, but a constraint on the geometry of space-time itself. Let's be precise about why. Special relativity, published by Albert Einstein in 1905, emerges from two postulates. First, the laws of physics are the same in all inertial reference frames, for any observer moving at constant velocity. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two simple postulates, an entire restructuring of our understanding of space and time follows. Time dilates. Moving clocks run slower than stationary ones. Space contracts. Moving objects are shorter in the direction of motion. Mass increases with velocity, and the energy required to accelerate an object increases as its velocity increases. approaching infinity as the object's velocity approaches the speed of light. That last point is the critical one. The relativistic mass of an object, the effective mass that must be overcome to continue accelerating it, is given by the Lorentz factor, which increases without bound as velocity approaches c, the speed of light. At 90% of the speed of light, the relativistic mass is approximately 2.3 times the rest mass. At 99%, it is approximately 7 times the rest mass. At 99.9%, it is approximately 22 times the rest mass. At 99.9999%, it approaches 707 times the rest mass. As velocity approaches c, the energy required to continue accelerating approaches infinity. To actually reach the speed of light would require infinite energy, and infinite energy does not exist in a finite universe. This is not a technological limitation. You cannot solve it with a better engine, a more efficient fuel source, or a more advanced civilization. The mathematics forbids it as absolutely as dividing by zero. But wait, does it forbid it absolutely? Because here is where physics introduces its own most intriguing complication. Special relativity prohibits objects from travelling through space faster than light. But it says nothing, at least not directly, about space itself moving. This distinction, subtle, profound, and deeply strange, is the crack in the wall through which theoretical physicists have been peering with increasing urgency for decades. In 1994, Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that sent a small shockwave through the theoretical physics community. Working within the framework of Einstein's general relativity, the more comprehensive theory that addresses gravity, acceleration, and the curvature of space-time, Alcubierre described a solution to Einstein's field equations that would allow, in principle, for faster-than-light travel without any object actually moving through space faster than light. The concept, which became known as the Alcubierre warp drive, works roughly as follows. Instead of accelerating a spacecraft through space, you reshape the space around the spacecraft. You compress space in front of the ship and expand space behind it, creating a bubble of flat space-time in which the ship sits, effectively stationary relative to its local space, while the bubble itself moves through the larger space-time fabric. Since the ship is not moving through space but riding in a bubble of space that is moving, the normal relativistic prohibition against superluminal velocity does not apply. In principle, the bubble could move at any speed, including faster than light, including, theoretically, much faster than light. On paper, the mathematics works. The Alcubierre metric is a valid solution to Einstein's field equations. The geometry is self-consistent, and for approximately 15 minutes after it was published, it seemed like the most important theoretical breakthrough in the history of space travel. Then the problems began to emerge, and they were severe. The first and most fundamental problem concerns energy. Creating an Alcubierre bubble requires exotic matter, material with negative energy density. In the normal world of matter and energy we interact with daily, all matter has positive energy density. Negative energy density is not something that exists in any conventional material. It requires a form of energy that violates standard energy conditions in quantum field theory, conditions that, while not absolutely proven to be universal, appear to hold throughout the observable universe. The quantity of exotic matter required by Alcubierre's original formulation was genuinely staggering. Early estimates placed it at roughly the mass-energy equivalent of Jupiter, negative. An amount of negative energy material comparable to the total mass energy of a gas giant, but with the opposite sign, would be required to create a bubble large enough to carry a spacecraft. Since we have never created or detected exotic matter in any quantity whatsoever, this represents a somewhat significant obstacle. Subsequent work by Harold White at NASA's Johnson Space Center in 2012 proposed modifications to the bubble geometry that would reduce the exotic matter requirements by orders of magnitude, potentially to amounts that might be achievable in a laboratory setting. White's group at NASA, operating under the EagleWorks Laboratories program, conducted experimental searches for microscopic space-time perturbations that might indicate warp field signatures. The results were inconclusive. No definitive evidence of space-time warping was produced, but the experiments were not sophisticated enough to rule it out either. Now here's where it gets truly strange. In 2021, As a paper by Eric Lentz at the University of Göttingen proposed a fundamentally different approach to warp drive physics, one that does not require exotic matter at all. Lentz described what he called soliton solutions to Einstein's field equations, self-reinforcing gravitational wave packets that could, in principle, carry a spacecraft at superluminal velocities using only conventional positive energy matter and fields. The geometry involved is extraordinarily complex. The paper describes a specific class of hyperbolic geometry solutions that had not previously been considered in the context of warp drive research. The theoretical physics community received Lentz's paper with significant interest and significant skepticism in approximately equal measure. The calculations are valid, but the energy requirements, while no longer requiring exotic matter, remain extraordinary, far beyond anything achievable with current or foreseeable technology. We are not talking about engineering challenges that a century of development would overcome. We are talking about energy scales comparable to the total energy output of entire stellar systems, required to be deployed in specific geometric configurations with extraordinary precision. These are not merely ambitious engineering goals, they are goals that may exceed the total energy budget available to any planetary civilization, period. But the Alcubierre and Lentz proposals are not the only theoretical escape routes from the cosmic speed limit. There is another concept that has occupied science fiction for decades and physics for nearly as long. A concept that, unlike the warp drive, emerges not from a deliberate attempt to engineer faster-than-light travel, but from a purely mathematical feature of general relativity that appeared in the equations almost immediately after Einstein published his field equations in 1915. The wormhole. Einstein himself, working with physicist Nathan Rosen in 1935, identified a mathematical solution to the field equations that describes a tunnel connecting two separate points in spacetime, what was initially called an Einstein-Rosen bridge, and what we now colloquially refer to as a wormhole. The mathematics is elegant, the same equations that describe the geometry of a black hole, a region of spacetime where gravity is so extreme that escape velocity exceeds the speed of light, also permit, in principle, a companion structure on the other side, a white hole from which matter and energy emerge. Connect a black hole to a white hole through a tunnel of curved spacetime, and you have a geometric shortcut through the fabric of the universe. A ship entering a wormhole at one location in space could, theoretically, emerge from the other end at a completely different location, potentially across the galaxy, potentially billions of light years away, without having traversed the intervening space at all. The ship never exceeded the speed of light. It simply travelled through a different path, one that happens to be much shorter. The theoretical appeal is obvious. The practical problems are, once again, severe. The Einstein-Rosen bridges described in the original 1935 paper are not traversable. They form and collapse on timescales so short that not even a photon could pass through before the throat pinches off. To create a traversable wormhole, one stable enough for a spacecraft to transit, would require, once again, exotic matter with negative energy density to prop open the throat against the gravitational tendency to collapse. In 1988, physicists Kip Thorne and Mike Morris at Caltech. Thorne would later win the 2017 Nobel Prize in Physics for his contributions to the detection of gravitational waves, published a paper explicitly analysing the requirements for a traversable wormhole. Their analysis confirmed that exotic matter would be required, but also identified the specific geometric configurations and energy conditions that would need to be satisfied. This was the paper that transformed wormholes from a purely mathematical curiosity into a subject of serious physical inquiry. Subsequent theoretical work, including a 2020 paper by Juan Maldacena of the Institute for Advanced Study in Princeton, building on insights from the ER=EPR conjecture connecting wormholes to quantum entanglement, has suggested deep connections between wormhole physics and quantum information theory that were not anticipated in the classical general relativity framework. These connections have not yet produced a practical pathway to traversable wormholes, but they have significantly deepened the theoretical understanding of why such objects are or aren't possible within the framework of quantum gravity. And quantum gravity, the still incomplete theoretical framework that attempts to reconcile general relativity with quantum mechanics, is the arena in which all these questions ultimately have to be answered. Let's pause for a moment and consider what this means at a human scale. We have spent roughly a century, since Einstein's publication of general relativity, developing the most sophisticated mathematical description of spacetime in history. We have used that description to identify two theoretical mechanisms, warp drives and wormholes, that appear to permit faster-than-light travel or communication without violating the specific prohibitions of special relativity. And in both cases, the universe has responded to our theoretical ingenuity with the same requirement: exotic matter, negative energy, something that doesn't exist in any form we have ever observed or created. Is this a coincidence? Is the universe placing the same specific obstacle in front of every apparent escape route as a matter of chance? Or is there something deeper operating here? Some principle of physics that we have not yet fully articulated that is systematically closing every door? Some physicists believe there is. The chronology protection conjecture, proposed by Stephen Hawking in 1992, suggests that the laws of physics conspire to prevent the creation of closed time-like curves, loops in time that would permit a traveller to return to their own past. Since a sufficiently advanced faster-than-light drive could, in some reference frames, and be used to travel backward in time, a consequence of special relativity's treatment of simultaneity, Hawking argued that any such technology would inevitably be prohibited by some as yet undiscovered principle of quantum gravity. In Hawking's characteristically dry formulation, it seems there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. The implication, stated with the gentle humour of a man who spent decades wrestling with the deepest questions in physics, is that the universe is not merely indifferent to our desire to travel between the stars, it is actively, systematically, perhaps even structurally opposed to it. And yet, there remains one more category of theoretical escape that we have not yet addressed. Was one that does not require exotic matter, one that does not require negative energy, one that requires only patience and a willingness to accept the most counterintuitive consequence of special relativity as not merely a mathematical abstraction, but a physical reality that can be engineered. Time dilation. Remember the Lorentz factor, the mathematical expression that describes how mass increases and energy requirements grow as an object approaches the speed of light. It has a companion consequence. As an object moves faster, time slows down for that object relative to stationary observers. At 90% of the speed of light, time passes 2.3 times slower for a moving traveller than for a stationary observer. At 99% it passes approximately 7 times slower. At 99.9999%, it passes approximately 707 times slower. In principle, at a sufficiently high fraction of the speed of light, say 99.999999%, the time dilation factor becomes so extreme that a traveller's subjective experience of a journey across the entire observable universe might be compressed to a span of years or even months, even as billions of years pass in the universe outside the ship. This is not science fiction. It is a direct, tested prediction of special relativity. Time dilation has been confirmed experimentally with atomic clocks on aircraft and satellites. GPS systems must correct for relativistic time dilation to function accurately. The physics is not in doubt. What this means, in principle, is that a traveller aboard a ship accelerating at a constant 1g, Earth-standard gravity, comfortable for human passengers, would reach Alpha Centauri in approximately 3.6 years of ship time, the galactic centre in approximately 21 years of ship time, the Andromeda Galaxy in approximately 28 years of ship time, the most distant observable galaxies in approximately 45 years of ship time. In terms of the subjective experience of the traveller, the universe is not prohibitively large. A human lifetime spent accelerating and decelerating at comfortable gravity could in principle traverse an enormous fraction of the observable universe. The catch, and there is always a catch in this particular story, is what happens when the traveller arrives. The ship experiences years. The universe outside experiences millions or billions of years. The civilization the traveller left behind has long since disappeared into history. The planet they were travelling to has potentially been dead for geological epochs. Whatever they find when they arrive is the product of eons of cosmic evolution that occurred while they were in transit, and if they wish to return home, The Milky Way they left is not the Milky Way they will find. Their solar system in all probability no longer exists. The Sun will have expanded into a red giant and consumed the Earth within approximately 5 billion years. For a journey to the Andromeda Galaxy, 2.5 million years of universe time, even if only 28 years of ship time, the travellers return to find a solar system 2.5 million years older than the one they left. Does a civilization spread across a galaxy through relativistic travel constitute a unified civilization? Can culture, language, memory, governance, or even biological identity persist across journeys where the ship ages decades while the civilization ages millions of years? The answer, examined honestly, appears to be no. Not in any form we would recognize as civilization. Not in any form that maintains the social, cultural, or even biological continuity that defines a society as coherent. Time dilation is not an escape from the cosmic prison. It is a transformation of the prison's character. Instead of confining you in space, it confines you in time. You can go anywhere and return to nothing you recognize. The implications of this discovery are almost too vast to comprehend, because what we are now forced to confront is not merely the engineering challenge of building a fast enough ship. We are confronted with the possibility that the universe's fundamental architecture, its speed limit, its expansion rate, its treatment of time and causality, is precisely configured to produce isolated pockets of intelligence, separated by distances and timescales that defeat any mechanism of connection, and that this isolation is not an accident, not a temporary condition awaiting a technological solution, but the permanent structural condition of any mind in this cosmos. In the summer of 1950, at the Los Alamos National Laboratory in New Mexico, 4 physicists were walking to lunch. The conversation had turned to a recent spate of UFO reports and a New Yorker cartoon that had gently satirized the idea. The 4 men were among the most brilliant scientists of the 20th century: Herbert York, Emil Konopinski, or Edward Teller, and Enrico Fermi. Fermi was, by any measure, a physicist of extraordinary insight, the architect of the first controlled nuclear chain reaction, a Nobel laureate, a man whose ability to produce accurate estimates from minimal information, what physicists still call Fermi estimation, was legendary among his colleagues. At some point during the conversation, after they had moved past the UFO jokes, Fermi went quiet. Then he looked up and asked, seemingly out of nowhere, "But where is everybody?" The question, as his colleagues immediately understood, was not about the UFOs, it was about the universe, about the probabilistic certainty, given the age and scale of the cosmos, that intelligent life should have arisen elsewhere, multiple times, perhaps millions of times, and yet no signals, no artifacts, no evidence of any kind that we are anything but alone. This is the Fermi paradox. Formalized over subsequent decades by scientists including Michael Hart, Frank Tipler, and Enrico Fermi's intellectual successors, it can be stated simply: if intelligent life is common in the universe, where is the evidence? Why haven't we been contacted? Why haven't we detected their signals, their waste heat, their megastructures, their probes? Dozens of proposed resolutions to the Fermi paradox exist. They range from the optimistic to the terrifying. Perhaps civilizations invariably destroy themselves before reaching spacefaring capability, the Great Filter hypothesis. Perhaps intelligent life is genuinely extraordinarily rare, and we are alone or nearly alone, the rare Earth hypothesis. Perhaps advanced civilizations deliberately go dark, avoiding contact for reasons we cannot fathom. Perhaps the universe is filled with signals we don't know how to detect. Perhaps we are in a cosmic zoo, observed but not contacted. Perhaps simulation theory. Perhaps something beyond our current imagination. Each of these hypotheses has been argued, modelled, and debated by scientists and philosophers for decades. But there is one resolution to the Fermi paradox that has received less attention than it deserves, not because it is less plausible than the others, but because its implications are uniquely uncomfortable. Not frightening in the dramatic science fiction sense, uncomfortable in the quieter, deeper sense of a truth that doesn't offer any path toward hope. The resolution is this: contact between civilizations is not merely difficult, it is, given the actual distances of the cosmos and the actual speed of light, impossible within any timescale that bears any relationship to the continued existence of either civilization. This is not the same as saying intelligent life doesn't exist. It is not the same as saying the universe is empty. It is saying something quite different and quite specific, that the universe could be populated with thousands, millions, even billions of technological civilizations, and that the distance between them, combined with the speed of light and the expansion of the universe, means that those civilizations are as effectively isolated from one another as if they existed in entirely separate universes. The prison hypothesis. Consider the mathematics carefully. For two civilizations to make meaningful contact, not merely to detect each other's existence, but to exchange information, to build a genuine communicative relationship, they must be close enough that a signal sent by one reaches the other in a time frame relevant to the continued existence of both. What does relevant mean? Let's be generous. Let's define it as the expected lifespan of a technological civilization, say, somewhere between 1,000 and 1 million years. This is a wide range, encompassing everything from a civilization that barely achieves radio technology before destroying itself, to one that survives to explore its solar system thoroughly before some catastrophe ends it. Frank Drake's original calculation in the Drake equation used various estimates for this variable, with results ranging from a galaxy hosting dozens to millions of simultaneous civilizations. For a signal round trip to complete within 1,000 years, the two civilizations must be no more than 500 light-years apart. Within 1 million years, no more than 500,000 light-years, still less than the diameter of the Milky Way. At first glance, these seem like manageable distances. The Milky Way contains hundreds of billions of stars within a disk 100,000 light-years across. Surely some civilizations exist within 500 light-years of each other, possibly. But here is where the numbers become devastating. The average spacing between stars in the Milky Way is approximately 4 to 5 light-years. But stars with the characteristics considered most favourable for complex life, G-type and K-type main sequence stars, C with stable habitable zones and long enough lifetimes for complex life to evolve, represent perhaps 20 to 30% of the total stellar population. The subset of those stars that actually harbour planets in the habitable zone with liquid water is unknown, but optimistic estimates suggest 10 to 20%. The subset of those planets that have actually developed complex life is utterly unknown. It could be near certainty, or it could be a fraction so small that we are the only example in the galaxy. The subset of planets with complex life that have developed technological civilization is similarly unconstrained. Multiply these fractions together, even with optimistic values for each factor, and the density of technological civilizations in the Milky Way remains extraordinarily low, perhaps 1 per thousands of cubic light-years of space, perhaps 1 per millions. The average distance between any two technological civilizations, if they exist at all in significant numbers, is likely to be measured in thousands of light-years at minimum. Thousands of light-years. For a civilization expected to last 1,000 to 1 million years, a signal from a civilization 5,000 light-years away takes 5,000 years to reach us. Any response takes another 5,000 years to return. A round-trip exchange of information takes 10,000 years. That is longer than the entirety of recorded human history, longer than the time from the construction of the Egyptian pyramids to the building of the International Space Station. And we're still only discussing signal exchange. Actual physical contact, a ship crossing 5,000 light-years, takes 5,000 years at the speed of light. With any realistically achievable propulsion, tens to hundreds of thousands of years. Some might wonder, couldn't a sufficiently advanced civilization solve this with technology we cannot yet imagine? Couldn't physics we haven't discovered yet provide the escape from the light speed limit that our current equations deny? This is a reasonable question. Intellectual humility demands we acknowledge the limits of our knowledge, but it demands equally that we take seriously what the knowledge we have is telling us. And what it is telling us is this. Every theoretical mechanism we have identified for circumventing the speed of light requires exotic conditions, negative energy, exotic matter, quantum gravitational physics beyond our current understanding, that may or may not be achievable in principle, and are certainly not achievable in any foreseeable practice. The theoretical doors are narrow, uncertain, and require keys we have never seen. Meanwhile, the distances are real. The expansion of the universe is real. The Hubble radius is real. These are not theoretical uncertainties. They are measured, confirmed features of the cosmos we actually inhabit. Here is the peak realization, the one that reorganizes everything. If the speed of light is truly an inviolable upper bound, which our best current physics says it is, and if the universe is truly expanding at an accelerating rate, which observation confirms, then the isolation of any technological civilization is not merely a present-day challenge awaiting a future solution. It is a condition that worsens with time. The cosmic prison is not static, it is tightening. Every year that passes, the Hubble radius, the boundary beyond which the expansion of space exceeds the speed of light, moves slightly inward relative to us. Galaxies that are currently on the edge of our observable universe will eventually recede beyond our reach entirely. In roughly 150 billion years, the only galaxies visible from the Milky Way, assuming the Milky Way still exists, will be those in our immediate local group. Andromeda, the Magellanic Clouds, a few dozen dwarf galaxies. Everything else will have receded beyond detection and beyond contact. The observable universe, the portion of the cosmos with which any form of communication is physically possible, is contracting. Future civilizations born in a cosmos far older than ours will have access to less of the universe than we do. They will look up at a sky containing fewer galaxies. They will have a smaller prison. And civilizations born in the very far future, trillions of years from now, in a cosmos where star formation has largely ceased, and the Milky Way's local group is the entire observable universe, will look at that small collection of galaxies and have no way of knowing that the cosmos is almost incomprehensibly larger. The evidence will have receded beyond detection. The prison walls will be invisible. The prisoners won't know they're imprisoned. This is perhaps the most genuinely vertiginous implication of the speed of light as a cosmic constraint. Not merely that we are isolated now, but that the universe is systematically reducing the information available to any future civilization about its own situation. The cosmos is hiding its own extent from those who will come to inhabit it. We are fortunate, in a strange way. We exist at a cosmic moment early enough to still observe most of the universe's galaxies. We have detected the cosmic microwave background, the echo of the Big Bang, which tells us the universe had a beginning and gives us access to its full history. We have enough information to piece together the large-scale structure of a cosmos that will eventually become inaccessible to direct observation. In 30 billion years, a civilization arising in the Milky Way, if any such civilization exists, will have no access to the cosmic microwave background. It will have receded beyond the observable horizon. That civilization will look out at a universe containing only a handful of galaxies, with no way of inferring that the cosmos was once far larger, far hotter, far more structured. They will have no way of knowing they live in what was once a universe, teeming with hundreds of billions of galaxies. They will think the universe is small, and they will be, in the only sense that matters to a creature trapped within its own light cone, correct. Let's bring this back to the question of contact with other civilizations. The Fermi paradox asks where everybody is. The prison hypothesis offers the following answer. They are exactly where we are, isolated, trapped within their own light cones, unable to cross the distances between civilizations at any speed that preserves cultural continuity, biological continuity, or communicative relevance. They are not hiding. They are not dead. They are not ignoring us. They are simply too far away for the universe's speed limit to ever permit contact. The silence of the cosmos is not evidence of emptiness. It is evidence of isolation, of a universe that, by the operation of its own physical laws, has divided its contents into an indefinite number of isolated islands, each capable of developing intelligence, culture, science, perhaps even an understanding of their own imprisonment, but permanently, structurally, inevitably separated from all the others. And yet, we keep listening. SETI continues. The Allen Telescope Array in California, the Breakthrough Listen initiative funded by Russian-Israeli entrepreneur Yuri Milner, with a budget of $100 million, using the world's most powerful radio telescopes to scan 1 million nearby stars and the centers of 100 galaxies. New radio telescope arrays being constructed across multiple continents. Every year, the search continues. Is this irrational? Is searching for a signal that physics suggests cannot meaningfully be acted upon? that any detected civilization is likely thousands of light years away, inaccessible in any practical sense. An exercise in futility? No. And the reason why is itself one of the most profound things that the prison hypothesis reveals about the nature of intelligence in this cosmos. Knowing you are not alone, even knowing it across a gap that cannot be crossed, even receiving a signal that cannot be answered within any meaningful time frame, changes something fundamental about the psychological and philosophical condition of an intelligent species. It transforms the existential experience of existence. We're not asking whether we can reach them. We're asking whether we are singular, whether intelligence is a freak accident of cosmic chemistry or a recurring feature of a universe hospitable to the emergence of minds. The answer to that question matters profoundly, regardless of whether the gap can be crossed. And if we ever do detect a signal, a genuine, verified, the unambiguous signal from another technological civilization, what we will have confirmed is not merely that they exist. We will have confirmed that the universe produces minds in isolation, separately, repeatedly, under the same laws. That intelligence is not an accident. That the cosmos, despite building a prison for every mind it generates minds anyway. That would be, in the full weight of the word, a revelation. Let's pause for a moment and consider what this really means. We have been speaking about the cosmic prison in terms of what it prevents, what it forecloses, what it denies, the contact that cannot happen, the journeys that cannot be completed in any meaningful human sense, the signals that arrive across thousands of light years to civilizations that may no longer exist. But there is another way to look at the same set of facts, a way that doesn't minimize the isolation or pretend it away, but that finds within it something unexpected, something that speaks not to cosmic indifference, but to a kind of unintentional structural intimacy between any mind and the universe it inhabits. Consider what it means for intelligence to arise at all within a cosmos so thoroughly designed, if designed is even the right word for a structure that emerged from physical law to isolate it. Every mind that has ever existed in this universe has done so in a prison. Every civilization that has ever looked up at the stars and wondered has done so from within the confines of its own light cone, its own Hubble sphere, its own temporal bubble, not just us, every intelligence, everywhere. The alien civilization 3,000 light years away, if it exists, is as enclosed by the speed of light as we are. The civilization at the center of the Andromeda galaxy, 2.5 million light years distant, is as bounded by cosmic expansion as we are. Whatever intelligence may exist in the Virgo supercluster, 65 million light years away, inhabits a prison of exactly the same character, differing only in the specific stars visible from its local vantage point. The prison is universal. The condition of isolation is the condition of intelligence in this cosmos, full stop. And within that universal prison, every mind that has ever engaged in scientific inquiry has arrived at the same fundamental discovery, that the universe is vast beyond navigation, ancient beyond comprehension, and governed by laws that apply identically regardless of where in the cosmos you happen to be standing. This is not a small thing. This is extraordinary. Every mind in the universe that develops physics, regardless of the planet, the star system, the galaxy, the biology, discovers the same speed of light, the same gravitational constant, the same fine structure constant governing electromagnetic interactions, the same Planck constant governing quantum behavior, the same laws of thermodynamics, the same space-time geometry, the same Big Bang cosmology. The prison has the same dimensions for everyone. The walls are made of the same physics, and that physics, when investigated with sufficient sophistication, reveals the prison's walls to be made of something that every civilization discovers simultaneously. The same mathematical structure. A civilization 3,000 light years away cannot reach us, cannot send a ship that would arrive within any relevant time frame, cannot exchange dialogue in any meaningful sense. But if they have developed physics, and the laws of physics are the same for them as for us, they have discovered the speed of light, they have derived special relativity, they have measured the expansion of the universe and confronted the same isolating implications we have. They are sitting with the same vertiginous recognition that the most brilliant thing their species ever produced, science, has revealed their permanent, inescapable solitude. We are in this sense connected. not by communication, by shared condition, by the universal experience of being a mind in a universe that is beautiful and vast and ancient and, in the most precise physical sense, unreachable. But this raises an even bigger question, and it is one that cuts to the deepest available layer of this entire inquiry. If the universe is structured to produce isolated intelligences, if every mind that arises is enclosed within its own light cone, unable to reach others, destined to develop and dissolve without meaningful contact, what does the universe gain from generating minds at all? This is not a theological question, it is a physical and philosophical one, because the universe, over 13.8 billion years of operation, has consistently produced environments hospitable to chemistry, chemistry hospitable to biology, and biology hospitable to intelligence. This did not happen by deliberate design. There is no scientific evidence for intentionality in the cosmos, but it happened. Over and over, wherever the conditions are right, matter organizes itself upward, toward complexity, toward replication, toward metabolism, toward sensation, toward cognition, toward the kind of mind that can ask why. And each such mind, upon achieving the sophistication to ask the deepest questions, discovers that it is alone. That the very speed of the universe's most fundamental phenomenon, light itself, is too slow to connect it to its peers. Is this irony? Is it tragedy? Is it simply physics, indifferent to the experiences of the creatures it produces? Physicist Paul Davies of Arizona State University has written extensively on the relationship between the universe's physical laws and the emergence of complexity in consciousness. In his analysis, the specific values of physical constants, including the speed of light, appear to be precisely tuned in ways that permit the existence of stable atoms, stable stars, stable planets, and ultimately biology. Change the speed of light significantly, and the electromagnetic interactions that govern chemistry become incompatible with the formation of complex molecules. Change it dramatically, and atoms cannot form at all. The speed of light is not merely a cosmic speed limit. It is one of the fundamental parameters that makes chemistry, and therefore life, possible. It determines the energy levels of atomic electron orbitals. It sets the scale of electromagnetic forces. It is woven into the structure of the matter at the quantum level in ways that make it not an arbitrary number, but a deeply constrained one. The prison is built from the same material as the prisoners, and here is the implication that sits at the edge of what current physics can address. The universe appears to require a speed of light approximately equal to what we measure in order to produce the stable chemistry necessary for complex life. But that same speed of light, combined with the scale of the universe and the rate of cosmic expansion, produces the isolation we have been describing. These are not independent features. They are aspects of the same underlying physics. The same value of C that makes carbon chemistry possible is the value of C that makes intercivilizational contact impossible. The universe cannot, within its current laws, have both. It cannot have chemistry and contact. It cannot have life and cosmic community. The same constant that builds the prison also builds the prisoners. This is not a proven theorem. It is a pattern that emerges when you hold the relevant physics together and examine them honestly. But it is a pattern robust enough that several serious physicists have written about it, not with despair, but with something approaching awe. Freeman Dyson, one of the 20th century's most creative theoretical physicists, spent decades thinking about the long-term future of intelligence in the cosmos. In his landmark 1979 paper Time Without End, Dyson explored how life and intelligence might persist in an expanding, cooling universe over cosmological timescales, thinking about minds that might operate at lower and lower metabolic rates as the cosmos aged, hibernating between thoughts for millions of years to conserve energy. Dyson's universe was one in which intelligence adapted to its prison rather than escaping it, in which minds found ways to persist within the constraints of physical law rather than transcending those constraints. Dyson's vision has been overtaken in some respects by subsequent discoveries. The accelerating expansion driven by dark energy was not known in 1979, and it complicates his long-term scenarios significantly. But the underlying orientation, intelligence adapting to and persisting within the cosmos's constraints, rather than overcoming them, remains deeply relevant. Because when we examine the actual trajectory of human civilization, in light of what we now know about the prison of the speed of light, Adaptation looks not like defeat, but like the only genuine option available. We're not going to cross the galaxy within any civilizational time frame. We're not going to exchange dialogue with civilizations thousands of light years away. We're not going to build an interstellar empire. But we can do something that may be, in the long assessment, more remarkable. We can understand the prison. We can map its walls with extraordinary precision. And we can describe the physics of its construction in mathematical language of such power and beauty that any other civilization in the universe, any mind anywhere that develops the same scientific traditions, would recognize the same equations. We can, in the only sense available to us, think our way across the distances that our bodies cannot cross. The history of science is, in this light, not merely a practical project of accumulating useful knowledge. It is the project of a mind engaging with the universe at the largest scales available to it, testing the bars of its cage not to escape but to understand, to know, with precision, what kind of universe it inhabits, to measure the walls and find in their measurements something extraordinary, that the prison is comprehensible, that the laws governing it are elegant, that the same mathematics describes the behavior of atoms in a laboratory and the recession of galaxies at the edge of the observable universe. A universe that produces minds and isolates them is strange. A universe that produces minds that can nevertheless comprehend the laws that isolate them is stranger still. And stranger still, almost unbearably strange when you sit with it, is the fact that those laws appear to be the same everywhere. Every mind in this cosmos, if it develops science, discovers the same prison, measures the same walls, derives the same speed of light, the same gravitational constant, the same cosmic microwave background temperature, the same Hubble parameter. We are alone, and we are, in the most profound and unexpected sense, in exactly the same situation as everyone else. There is one more dimension of this story that deserves careful attention, because in all our discussion of the speed of the light as a constraint, as a prison, as an isolating principle, we have not yet addressed what may be the most remarkable response to that constraint ever produced by human civilization. We have begun sending physical objects beyond the solar system. The Voyager 1 spacecraft, launched in September 1977, crossed the heliopause, the boundary of the Sun's influence, where the solar wind gives way to interstellar space, in August 2012. It is currently approximately 23 billion kilometers from the Sun, travelling at approximately 17 kilometers per second. At this speed, Voyager 1 will reach the vicinity of the nearest stars in approximately 40,000 years. 40,000 years. A round-trip communication with it, at radio frequencies travelling at the speed of light, already takes approximately 45 hours one way. A round-trip exchange takes nearly 4 days, and it is still within our solar system. On board Voyager 1 and its twin, Voyager 2, is a gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. Music, greetings in 55 languages, scientific diagrams, images of human beings in the natural world. A kind of message in a bottle thrown not into an ocean but into the interstellar medium. The chances of any civilization intercepting Voyager, one within any relevant time frame, are, when examined honestly, infinitesimal. The spacecraft is not aimed at any particular star. Interstellar space is vast. The probability of a chance encounter with another civilization is so small as to be effectively zero on any timescale shorter than galactic epochs, and yet it was built and launched and carries its golden disk into the dark. Not because any rational calculation of probability justified the effort, but because the impulse to reach across the prison's walls, even symbolically, even knowing the walls cannot be crossed, is apparently intrinsic to a mind that understands its own isolation. The golden record is not a practical communication strategy. It is an act of defiance, an insistence against every physical constraint that this civilization existed, thought, created, wondered, and reached. That the prison could not prevent the gesture of reaching, even if it prevents the reaching itself. That, perhaps, is what intelligence does in a universe built the way this one is. It recognizes the cage, it maps the bars, and then it reaches anyway. We began with a fact so familiar it felt like furniture. Light travels fast. Everyone knows this. It is among the first things any scientifically literate person learns. And then we followed that fact, carefully, honestly, without flinching from what it implies, into the structure of space-time itself, into the expanding universe and the accelerating recession of galaxies beyond any hope of contact, into the mathematics of warp drives and wormholes and time dilation, and the stubborn, systematic obstacles that physics places in front of every theoretical escape, into the Fermi paradox and the possibility that its resolution is not dramatic but architectural, not that the universe is empty, but that its speed limit and its expansion rate combine to produce a cosmos of permanent structural isolation, into the strange, counterintuitive insight that the same physics that builds the prison also builds the prisoners, that the speed of light is not an arbitrary cruelty but a parameter woven into the fabric of atomic chemistry and electromagnetic interaction, that without it, precisely as it is, matter as we know it could not exist. And into the deepest available question, what does it mean to be a mind in a universe that produces minds in isolation, separates them by distances their own physical laws forbid them to cross, and yet endows them with the capacity to understand the full extent of their confinement? What it means, as best as we can currently determine, is this. Every civilization in this cosmos that reaches the level of sophistication necessary to detect its own isolation also reaches the level of sophistication necessary to understand why the isolation exists. The same science that reveals the prison reveals its architecture. The same minds capable of feeling the loneliness are capable of comprehending the physics behind it. This is not comfort exactly. The isolation is real. The distances are real. The speed of a light is real, and its inadequacy for intercivilizational contact at the scale of this universe is as real as any fact in physics. But there is something in the comprehension itself, in the capacity of a mind to understand the full geometry of its confinement, that seems important. Something that changes the character of the isolation without eliminating it. One thread remains open, unresolved, demanding continued attention. We do not know whether the universe is full of civilizations or nearly empty. We do not know whether the great silence we observe is the silence of cosmic loneliness or the silence of cosmic isolation. Whether we are not hearing others because there are no others to hear, or because the speed of light makes their signals irrelevant at the distances involved. These are different situations with different implications, and distinguishing between them, empirically, scientifically, with the tools of radio telescopes and optical surveys and next-generation space observatories, is among the most important projects available to any civilization at our stage of development. As we continue to extend our instruments into the cosmos, as SETI expands and deepens its listening, as new physics potentially opens questions about the nature of space-time that current theories leave unresolved, we continue to probe the walls of the prison, not because we expect to find a door, but because understanding the walls is for a mind its own form of reaching, and reaching, even into the permanent dark, is what minds do.